Hello, and welcome to this video demonstration of the IBM Internet of Things solution. My name is Justin Dyer, and I'm a System Solution Architect at IBM. In this demonstration, we will see how we can design, monitor, and improve connected systems utilizing the IBM platform for building and managing IoT solutions. We will take a look at how we can augment traditional systems engineering with designing for analytics. That is, defining monitors and the key data points we want to monitor once a system is deployed, and then feeding the insight we can gain by analyzing that data back into engineering in order to make our connected systems faster, safer, more reliable, more secure, and more optimized. In a sense, enabling a feedback loop around engineering, deployment, and operations to continuously fine-tune, calibrate, and improve our connected systems. To help put the demonstration into context, we will explore a fictional solar energy company that is looking to break into a new market by providing solar as a service to the New England region. In order to reduce initial entry costs for their customers, they maintain ownership of the infrastructure equipment, such as the solar panels, inverters, and batteries, and only charge for installation and monthly service fees. This will allow their customers to realize the value of solar energy by reducing their electric bills without the expensive upfront costs of buying all the equipment. The monthly service fee also includes excellent customer support and maintenance of the installed equipment. Desiring to be the first to market with solar as a service and capitalize on the opportunity, they realize they need help from IBM to design, monitor, and improve their existing solar energy systems. IBM's IoT solution combines the power of continuous engineering, analytics, and asset management to help give them a leg up on the competition. Here we can see an overview of the IBM IoT solution. We will use this graphic throughout the demonstration to provide context as to where we are in the designing, monitoring, and improving of our things. In this first chapter of our story, we'll take a look at a real physical device and its interaction with a cloud application via the use of the IBM IoT Foundation services. Let's start by looking at the actual connected device we will design and monitor throughout this demonstration. We can think of this device as the solar energy controller for our solar as a service system. It uses a Raspberry Pi with a connection to a sensor breakout board that can read the voltages and currents from both a lithium battery as well as a mini solar panel. IBM's IoT Foundation service provides recipes which allow us to easily register and connect any device or sensor to a fully managed cloud-hosted service that is designed to simplify and derive the value from our IoT devices. Here we can see our devices communicating with a cloud application that has an HTML user interface we can access from a tablet or smartphone. The gauges represent different power measurements, and covering or uncovering the solar panel causes the solar voltage to fall or rise. IoT Foundation services allow us to securely capture and store this data from our connected system. This is an important first step. However, what we do with this data is where we will truly see value from our connected system. What we just viewed was a real physical device communicating to a cloud application via the IBM IoT Foundation services. But how did we get there in the first place? In this next chapter, we'll explore how system engineering plays a critical role in the development of IoT devices. Let's do some design exploration and see how we can model and simulate our IoT system. Not just the devices themselves, but the sensors, cloud apps, and clients they interact with. We are now taking a look at the high-level architecture modeled in the IBM Internet of Things Workbench. IoT Workbench is a service for designing, constructing, and simulating Internet of Things systems consisting of devices, cloud services, and clients. It focuses on visual designs using diagrams and rapid simulation of multiple devices over the IBM Internet of Things Foundation. Our Solar as a Service company is utilizing IoT Workbench for design exploration. It helps us define and simulate various configurations of our end-to-end system, including multiple device instances. Here we can see how our device is connected to multiple sensors and cloud applications. Our Solar as a Service system will need to acquire forecast information from a web service in order to help determine when to use power from a solar battery versus power from the grid. We can see here the attribute defined for holding the forecast. We can also model the message communication to our cloud apps. In this case, we're using the industry standard MQTT protocol for message communication. MQTT is designed for efficient exchange of data to and from the devices in real time. Another key capability of IoT Workbench is its ability to generate Node.js and Node-RED applications. These are skeletons which can quickly get us up and running with cloud apps for our Solar as a Service system. Let's now have a look at some of the simulation capabilities. Here we can do some rapid prototyping to see how our devices will interact with our cloud application. We can simulate any number of devices. In particular, we are having a look at a simulated device in Arizona and can see that our device has acquired the current forecast for that area. We can also use our HTML client user interface to control the simulated device by switching its power mode from utility to solar. IoT Workbench allows us to generate HTML clients automatically for quick testing of the behavior. We can change attribute values on the fly and see how that affects the system. For example, if the solar battery has no charge, then our system should automatically switch back to utility power mode. By use of the simulation, we can see that the system does not work as we expected. Let's make a change to the behavior to ensure our Solar as a Service system switches over to utility power when the battery charge falls below 10%. We can open up the behavior for our device and inject some JavaScript code, make sure our system correctly switches over to utility power mode. This capability of design exploration allows us to identify issues in our system early in the development lifecycle. To test this change in the behavior, we simply switch back to the Simulation tab. And we can see that our power mode does indeed now switch over to utility mode as expected. Now that we have done some rapid prototyping, let's take a deeper dive into the development of our system by first having a look at the requirements. We just had a look at performing some system engineering using the IoT Workbench tool. In this next chapter, we will begin to dive into the design and engineering of our connected thing. We can use the behavior and interfaces we discovered in IoT Workbench to help drive the requirements and specifications for our device. Let's explore some of the requirements for our Solar as a Service controller. A solid foundation of any good system starts with good requirements. We can explore the requirements for our Solar as a Service system using Doors Next Generation. The IBM Continuous Engineering solution excels at managing requirements and traceability. In particular, we will focus on the battery life and optimal environment for the battery installation. In the Internet of Things, monitoring and analyzing the data from our connected devices can be a key differentiator in our business outcomes. As such, it's becoming increasingly necessary to design for analytics. That is, thinking about and involving analytics early in the development lifecycle, using requirements to ensure monitors are put in place, and feeding historical data and analytics back into system engineering. This can provide engineers with valuable insight to help guide them in making future systems faster, better, safer, and more optimized. For example, we may want to monitor a number of data points and create rules to take actions when certain conditions occur. We have a requirement here that states the system shall send an alert if there is no voltage coming from the solar battery. An engineer can easily create a rule to monitor this condition. These monitors can then be automatically created using an integration to IBM Real-Time Insights. Once the devices themselves are deployed, the monitors can be activated and used to take automated actions based on emerging conditions. Navigating into Real-Time Insights, we can see the new rule has been created. We will take a closer look at Real-Time Insights in a following chapter. For now, we can see the rule has been put in place and we can activate it once our connected system has been deployed. We just had a look at managing requirements and creating monitors using Doors Next Generation. Based on the systems engineering we did earlier and the requirements captured for our connected device, we can begin to take a look at the detailed design of our embedded controller. In this next chapter, we will see how we can apply model-driven development using the Unified Modeling Language and Rhapsody. Here we can explore the detailed design of our embedded controller for our device in Rhapsody. The IBM Continuous Engineering solution provides tools for both model-based systems engineering as well as model-driven development for embedded software, both of which utilize standard graphical notations such as the systems and unified modeling languages. Models can be executed to help flush out defects much earlier in the product development lifecycle, and production quality code can be generated from the models specifically tuned to real-time embedded platforms. In this example, we are using Rhapsody to model the control logic for our connected devices. With the push of a button, Rhapsody can push the code down to our physical device and start it up. With Rhapsody's model execution capabilities, we can see the model come to life while the device is running. Views such as sequence diagrams and state machines show us the communication of messages flowing back and forth between the various components of our system, as well as states or modes our system is in. This ability to do continuous verification as we develop our system is a cornerstone of the IBM continuous engineering solution. We can debug the design and examine data values while our physical device is communicating with our cloud app. This helps us explore different designs and identify critical defects early in the development lifecycle. Now that our solar power controller is up and running, let's take a look at how we can analyze the data coming from the device. We just had a look at the detailed design and now have the device up and running in a deployed New England location. In this next chapter, we'll explore how we can monitor data coming from the device using real-time insights. We will see how the data can be analyzed and rules can be put into place to take automated actions triggered from emerging conditions. If we remember from a previous chapter, we used Doors Next Generation to put some monitors in place to send alerts when certain conditions occur on our connected devices. We will now see how Real-Time Insights activates those monitors and allows us to visualize what's happening in real time and respond to emerging conditions through automated actions. Since our Solar as a Service company has goals to provide excellent customer service and make sure their equipment deployed at customer locations is performing as expected, we will make use of Real-Time Insights' ability to apply rules to the data and take automated actions. For example, if a solar battery installed at a customer location showed a low voltage or no voltage at all, it could mean the battery is either malfunctioning or nearing its end of life. We would want to be alerted of this type of condition right away so we could proactively send out a technician to inspect and fix the issue. Here we can see the rule and action constructed for catching this kind of scenario. Once created, the rules can be activated. We will put this rule into place to monitor our New England Solar as a Service systems. To see this rule in action, let's have a look at how the climate changes in New England cause problems for our existing solar batteries. One easy way to test a dead or malfunctioning battery on our device is to simply unplug the battery. This will cause the battery voltage reading to eventually drop to 0 volts. Once this condition has occurred, our real-time insight rule should kick into place and alert us of this condition. Let's have a look back in Real-Time Insights dashboard to see this alert. Here we can see the alerts dashboard in Real-Time Insights. Highlighting the most recent alert, we can see where our device triggered the alert when the battery voltage dropped to 0. We can also see a number of other data points captured with the alert, including the ambient temperature at the time the rule was triggered. Next, let's see how our Solar as a Service company can take an automated action to proactively send out a technician to the customer's site to inspect the issue. We just had a look at monitoring and applying analytics to the data coming from the device. Our Solar as a Service company may have thousands of these devices deployed, along with the solar equipment, such as the panels and batteries. So how do we manage all of these assets? In this next chapter, we will see how we can use the IBM Asset Management solution to track and maintain our connected systems. One of the actions triggered by the no battery voltage rule was to automatically create an incident or service request in IBM Maximo, an asset management solution. Our Solar as a Service company is using Maximo to track and manage all of their deployed assets. For example, the solar panels, batteries, and power inverters at each customer's location. In addition to asset management and many other capabilities, Maximo provides work management as well, managing both planned and unplanned work activities from initial request through completion. Here we are seeing the data that was captured automatically when the real-time insight alert occurred, including the various data points and the ID and location of the asset in question. This allows us to trigger a work order to send a technician out to the customer site to examine the issue closer. Maximo also provides dashboards with an ability to see key performance indicators captured from our assets. Here we can see a KPI chart for our solar batteries installed in the New England region. This points out a disturbing trend. A number of batteries are failing at a rate faster than we expected. This information, combined with data points captured from the real-time insights alerts, points out a major problem with the batteries installed in New England. We need to feed this information back into engineering right away so the issue can be corrected. We just had a look at managing and maintaining our assets using IBM Maximo. It is vital that information gathered from analytics, diagnostics, and maintenance be communicated back into engineering in order to improve our connected systems. In this next chapter, We will see how the IBM collaboration and change management solution can be used to ease the communication of information between operations and engineering. Let's now have a look at how this information regarding the failure of batteries in New England can be fed back into engineering. The IBM Continuous Engineering solution provides a strong collaborative environment for change management. Here we can see a defect has been created against the Solar-as-a-Service systems in New England. The defect contains information gathered from both real-time insights as well as maintenance records. It turns out, based on work order logs from technicians, that a majority of the batteries that failed were installed in unheated areas, such as garages, and as such were exposed to cold temperatures during the winter months. The defect can be further augmented with information by attaching reports generated from maintenance records, showing all the incidents reported against the failing batteries in New England. With all the information we need to investigate the problem, we can now assign this defect to a system engineer and begin working on identifying and fixing the issue. We can see that the defect has been further enhanced with information pointing the system engineer to the original requirement the battery voltage monitor was linked to. Clicking the link navigates the engineer to the requirement where a closer inspection can be made. The system engineer now has the power to inspect data captured from the connected systems whenever the monitor is triggered. Utilizing the real-time insights integration, we can call up a graph showing this data. The graph shows historical data points correlating the ambient temperature of the battery each time a deployed device triggered the associated no battery voltage alert. This is extremely valuable analytical feedback from devices deployed in the real world that engineers can use to gain insight as to why the batteries are failing in the New England region. Just knowing the voltage of the battery at the time of failure is not enough. It is only when we see this data combined with other data points, such as the ambient temperature, can we start to identify a pattern. Using this data, the system engineer has narrowed down the problem to a specific requirement, defining the temperature thresholds for where the battery is installed. This discovery could then lead into a new system change request, where a trade study can be performed to determine the best solution. Perhaps replacing lead-acid batteries in the existing systems with lithium-ion batteries in order to handle the colder temperatures in the New England region. By leveraging the sensor data and analytics from all their connected devices, our Solar-as-a-Service company was able to improve their systems. In effect, connecting design, test, and operations data with analytics in order to enable a closed-loop engineering process for the Internet of Things. This now concludes this demonstration of the IBM IoT solution. Hopefully you have seen how this solution can help you design, monitor, and improve your connected systems and devices. To learn more about IBM's point of view on the Internet of Things, or to try it out for yourself, please visit our website. Thank you for taking the time to watch this video, and look for more videos on this and similar topics in the future.